Thank you, by the way. As you can see from the photo and from the affiliation, I came a short distance today. I've been up here several times for these symposia, and they've been really great. I appreciate that, and I appreciate being invited to be a speaker here. Today, my topic is going to be spectral analysis of electrocorticography in humans. And I don't teach this topic, unlike Jonathan, and my talk's a little shorter, so there may be less kind of nitty-gritty practical advice, but I hope that there will be some conceptually useful overviews and some new thoughts. So the outline is first I'm going to give you an introduction, tell you what this method is, what we do with it, and then I'm going to talk about some spectral motifs that we see in electrocorticography data. Well, I'll just tell you, it's intracranial EEG. I'm going to talk about 3 types of spectral motifs and then talk about the relationship between electrocorticography, field potentials, and functional MRI. And I will start with an overview. This is a slide I got from Matti Hamalainen, who spoke here in November. And he had this nice image of a 500-channel EEG and MEG illustrating the proximity of the sensors to the head. The MEG sensors are considerably further away because of the machinery in the device. Electrocorticography is effectively the same technology as EEG, but it goes under the skull instead of on top of the skull. And so that's a kind of schematic brain showing a grid of electrodes placed under the skull on a CT image. It's done in patients, and I'll tell you about that in a moment. Schematically, you can see that the electrode sits on top of the gray matter underneath the skull and underneath the dural tissue, so it is quite close to the brain. So this is an invasive technique. It's not used in volunteers. It's used in pre-surgical clinical subjects who are usually undergoing brain surgery for drug-resistant epilepsy, though there are other cases. And the patients get an array of electrodes implanted to record their brain activity for about a week while they're in the hospital in order to measure brain tissue, figure out what's healthy and what's not, and also to specifically diagnose the locus of the seizure. So they're in the hospital for about a week with the medical staff waiting for the patient to have a seizure so they can figure out where the locus is. So now I have a kind of graphical image. If you're squeamish about blood, then look away for a moment. This is a patient who's had the skull and dura removed to implant electrodes. This is a grid of electrodes implanted on the same brain. And here's a scale bar. They're placed about typically 1 centimeter spacing, center to center. And they're about 2.3 millimeters in diameter of exposed electrode, which corresponds to something like 500,000 neurons sitting in a column of tissue underneath that electrode. Now, the interesting thing for basic science is that during the week that the patients are in the hospital, they're kind of okay. They're in the hospital room. You can visit them. If they agree, they can volunteer to participate in cognitive or perceptual experiments of various kinds. You go, you bring a laptop in, you do your experiment, and they have this rig hooked up to them that you can record from. One of the important things about that is that if we're doing basic research and we're not studying epilepsy, we want to be sure that there are electrodes over parts of the brain that are not epileptic. And that typically is the case. The signal we're going to pick up is similar to the signals that Matti Hamalainen talked about in November, the EEG signal. I'm not going to say too much about it other than the dendrites in the pyramidal cells are thought to contribute to the signal through their currents. Here's an example of a rendering of the right hemisphere of one of our subjects, you can see that they've got on the order of 100 electrodes. The actual source of the epilepsy is rather small, and so we've got a large swath of healthy brain that we can study. The precise locations where these electrodes go will vary from subject to subject. They'll always be in one hemisphere, as far as I know. You never see it in both hemispheres in the same subject. This is one example subject over the period of about 3 years of study at the Stanford Human, this is called SHISA. We suggested they come up with a better abbreviation than this, but that's what we've got. The Stanford Human Intracranial Cognitive Electrophysiology Program. And these are all the electrodes that were used in studies from different patients projected onto one brain in a template space. And you can see that it gets pretty good coverage of the brain, most of the brain, but some areas more than others. You get a lot of coverage of the bottom, the ventral temporal lobe, not a whole lot in the occipital pole, although you do get some electrodes over visual cortex. I do vision science, so that the patients who have electrodes there are useful for me. So I had a little poke using PubMed's tool that lets you see how often terms are searched for on Pub. Not how often they're searched for, how many publications there are that correspond to particular search terms. And looking for ECoG, or electrocortographic or electrocorticography, or intracranial EEG, the publications went from around 0 and started rising around 1990 and have been rising quite a bit lately. There's a lot of increase in the interest in using ECoG these days. And for comparison in red, I put EEG, which is a much bigger number but has a slower rise. And there are a couple of time points on here that I think are interesting. I don't quite mean to have this exact level of precision by this arrow, but in the 90s, there were a number of investigations of what we sometimes call category selective cortex in the ventral visual system with evoked potentials using intracranial EEG. And that was a kind of exciting finding that you could find specific parts of the brain that were selective for faces or for objects or for other types of stimuli. And that spurred some interest. I'm going to show you one result from that, which is here. This is from a group at Yale. A number of faculty collaborated on this work. And these are the positions of a strip of electrodes. And on the right are plots. These are evoked responses, which means you show a stimulus many times, and then you average the response to that stimulus. And it's showing the responses from 4 electrodes, 9, 10, 11, and 12. And the 2 yellow ones, 10 and 11, here in the middle, have a big response for faces more than other stimuli. The ones right next to it, 9 and 12, do not have that kind of selectivity. So this shows you one of the benefits you get from this kind of measurement, which has very good spatial resolution compared to MEG or EEG. And there were a number of findings like this in the 90s. I think it got some interest, but I think it also got swamped by fMRI in that decade, which investigated many of these other areas without having to wait for patient volunteers with electrodes in just the right place. And then I think around here, there was another increase in the interest in this method. And I think that 2 things happened. One is an interest in BCI, brain-computer interfaces. And I suspect that has to do with the improvement in computer technology to do real-time analysis of the signal. ECoG signals are very good for BCI because if you have a patient who is, let's say, paralyzed and you want to implant or somehow read out their brain signals in order for them to control a robotic arm, then you want them to be able to do that on every trial. You don't want to have to average 50 attempts to read the signal. So you need very good signal to noise, and you probably need good spatial resolution, and you don't want the signals to fall apart if you happen to walk by a TV or a microwave. So even though it's a very invasive technique, it has a lot of promise for BCI. That's all I'm going to say about that. The other thing that happened in the kind of, what do they call, the aughts, is a change in emphasis in the signal processing and the analysis of the ECoG signals, and that's what I'm going to focus on for the rest of the talk, in particular, spectral analysis. And the idea that is often out there in the field, and I kind of have had this in the back of my mind as I was working on this talk, is that when people measure electromagnetic signals from the brain, in this case, let's say an ECoG signal, they'll often take the Fourier transform and look at it in the Fourier domain, the power or the amplitude spectrum, and then divide that signal up into bands. And we saw in some of the talks in November, these bands exist because rhythms, prominent rhythms, were found in certain frequency ranges, first the alpha and beta band by Berger in the 30s, and later some of these other bands. What sometimes happens now in the field is that people look at the power in one band, in the beta band or in the alpha band, and use that as a proxy for some kind of biological circuit or cognitive process. And the point I'm going to be harping on for the rest of this talk is that biological processes don't have to respect the frequency bands. And they can disrespect it, so to speak, in two ways. You could have a process that spans many frequency bands. It's not confined to a band. You could also have multiple processes within one band, and measuring the power in that band may mislead you if you want to attribute it to a single process. So I'm going to talk about 3 cases of spectral analyses and show how that relates to this picture of looking at signals in terms of their spectra. And I'm going to start with the steady state signal, steady state evoked potentials. And this is a case where the frequencies in the signal are largely determined by the experimenter because they put the frequencies into the stimulus. So what I've got here is a stimulus that we have shown to a number of our patients, which flickers at a particular frequency. In this case, it flickers, it reverses contrast 15 times a second, and it would go on for many seconds, and then it would be gray. I sped it up. And because the stimulus is reversing 15 times per second, and because the visual system is highly responsive to changes in contrast, we're going to expect the visual system to respond vigorously 15 times per second. And we'll therefore measure the ECoG response at the input frequencies as well as the harmonics, 15 hertz, 30 hertz, 45 hertz, and so forth. And I'm going to show you an example here of data. This is an electrode from primary visual cortex. This is the back of the brain, the right hemisphere. This is the calcar sulcus, where primary visual cortex is located. And this is an electrode on the superior bank of the calcar sulcus. And we've got 60 seconds of data. This is 1 second long, so we've epoched it into 60 epochs. And the red is the mean, and the black traces are the individual trials. And I think you can get a sense that the individual trials are not bad. They're not the same as the mean, but you can see the pattern without averaging. And you can see it more clearly if you take the signals and you transform them into the spectral domain. And in particular, we see the average spectrum. So we take each second of data, we compute the Fourier transform, we take the amplitude spectrum, and we average the amplitudes. And at 15 hertz, which is the stimulus frequency, we get a really big response. And we also get that a big response at 30 hertz and higher harmonics. I've removed the line noise here, 60 hertz and 120 hertz with a very cheap hack, just completing right through it. Okay. So This is the amplitude spectrum. You can see the first few harmonics are quite large, and the peaks are quite narrow, and they're kind of across the spectrum. They're not in one place. They're spread out every 15 hertz. And if you look at this, exactly the same data, sorry, that's called the steady state visual evoked potential, and that's the background EEG, the frequencies in between the harmonics. If you take the same data and you plot it on a log scale on both axes, you see a couple of interesting things. One thing is that the spectrum is approximately a straight line. Straight line on a log-log axis means it's a power function. The other thing you can see is that these peaks go quite high. Even though the amplitude here is quite low, this is a log scale, so these are very small numbers, it's still pretty big compared to the noise on either side of it, and that's going up to 135 hertz. And just, yep.
How much do you know about coupling between the neurons and the electrodes? Like, do you know, does the resistance vary between electrodes? Do you know if that filtering is to do with capacitive coupling?
Yes, the answer is it does, and I actually meant to say something about that when I showed you the brain image, but I didn't dwell on it. Sometimes the electrodes are partially sitting over vessels, and sometimes they make a good contact with the cortex. Sometimes they sit over a sulcus, they span a sulcus, and those things matter. And if you wanted to do something like estimate the exponent in this power law, you'd want to make sure you're avoiding electrodes, for example, that are sitting over vessels. And just to give you an intuition, by the way, for why we see these higher order harmonics, you can see that the actual time series is not a perfect sine wave. It's a little bit squarish, and that kind of squarish shape, loosely speaking, is what corresponds to these harmonics. So I want to do a little bit of interpretation, and this is partly to contrast with what's going to follow. The interpretation here is that the steady state visual evoked potential, we call it steady state because the stimulus is just flickering and the brain gets into a nice steady state where it's responding in the same way over and over, reflects a population of neurons which are time locked to a stimulus. Those are those peaks at the same frequency as the stimulus, and hence the neurons are at least approximately synchronous with each other. It's a very large spectral response, which you could see in the Fourier transform. It doesn't have to be a very large neural response as long as the responses are synchronous. And that's because a modest-sized neural population that's all doing the same thing will contribute to a large signal over the background if everything else is asynchronous. Okay, so this is one type of spectral analysis that we do that's not confined to one specific band. I want to show you another analysis that actually comes from the same experiment and from the same data set. I cheated a little bit when I showed you this because I didn't show you what happens when there is no flicker, when the subject's looking at a blank screen. And you might have guessed that it would look just like this, except without the gray peaks. But that is not the case. In addition to lacking the peaks, when there's no stimulus, there's also a broadband difference across the whole frequency spectrum that we can measure. When there's a blank stimulus, the response has a lower amplitude compared to when the stimulus is flickering. And why is that? Before I answer that, I'll just make a couple of observations about it, which is that the responses between the stimulus harmonics, like over here, say, are asynchronous with the stimulus. Because the stimulus is flickering at 15 hertz, not at 18 hertz. It's just not synchronous with the stimulus. So they're not time locked to the stimulus events. The shape of the spectrum, the fact that it's a straight line in this log-log space, provides a possible clue. A power law suggests a noise-like process or a random walk. If you take white noise data and you do a cumulative sum, or if you just do a random walk and plot the spectrum of the positions, you'll get something that looks like this. So how can we interpret that in terms of the underlying neuroscience? I'm going to offer you a model published by a friend of mine, Kai Miller, several years ago, who thought a lot about this power law. He's the one who also measured the electrodes over blood vessels and over cortex to distinguish, to get an accurate measurement of the spectrum. If you take, let me first give you a one-sentence preview. If you take kind of random inputs and you put them through a leaky integrator, you'll get something like that spectrum that we saw. A spectrum that falls off in a straight line with the log frequency. If we think about that physiologically and we take some action potentials which have let's say a Poisson distribution or white noise distribution, each one that arrives causes some current to enter the neuron, and the charge in the neuron, we have a postsynaptic current. That current spreads down the dendrite, the charge builds up, and there's some leakage out of the neuron in proportion to the charge accumulation. And that current then is what produces the field potential that we measure. And if you simulate this by simply taking Poisson inputs and put it through postsynaptic currents and a leaky integrator, you will get something like this. This is a simulation with 10 spikes per second arriving at each synapse. The interesting thing is that if you do the simulation again, but now put a higher Poisson rate, so more spikes, you get this broadband shift that kind of looks like the data we saw. Okay. And so if we then reason backwards and we say, well, when we see this kind of shift, we're going to interpret it as a change in the spike rate, that now gives us an interesting interpretation of this data, which is that this broadband spectral change may be a good correlate of a change in the local spike rate. Okay? And so the interpretation here is that the broadband signal reflects a population of neurons responding asynchronously to a stimulus or behavior. It's likely not an oscillation. People will sometimes call this high frequency or high gamma signals for those in the field. I think it's probably not an oscillation, but it's hypothesized to reflect the noise distribution of spikes. I showed you an example from visual cortex. There are examples throughout the brain measured with ECoG. It's a very robust signal. Here's an example from motor cortex. Here's an example from primary visual cortex with a static stimulus rather than a flickering one. And here's an example from ventral temporal cortex. In each case, the stimulus or the action compared to rest causes a broadband spectral change. So I said a moment ago that people don't always call it that, a broadband spectral change. They sometimes call it a high gamma signal or even high gamma oscillations. And this is kind of one of the reasons. This is data showing the spectrum to a stimulus in magenta compared to a bad stimulus for this particular electrode or rest. And you can see that the biggest change is in the higher frequencies. If you look in the lower frequencies, there's a much smaller effect. So that doesn't quite look as broadband as I made it sound like. And one interpretation is that's because there's multiple processes going on here. And one way to get at that is to use the data to try to infer what these processes are. And in a 2007 paper, also by Kai Miller, in an attempt to uncover a broadband signal, he did a principal components analysis on the spectra, on the log spectra, after normalizing them. And what that reveals is the patterns in the spectrum that covary together across a data set. And if you do that, you find that one principal component, shown there in red, looks like this broadband signal. There happen to be other components that have low frequency signals or other rhythms that are interacting with this, so that you might not see this as a broadband elevation across all frequencies, but it may be there implicitly. If you remove the second and third principal component and put everything else back, you get something that looks like a nice broadband signal. Okay, so that's two types of spectral analyses and kinds of spectral data. There's one more I want to mention, which is induced oscillations. We heard a fair amount about this from in November from both Matti Hamalainen and Oostenveld, so I'm only going to speak about it briefly. And in fact, we saw an example kind of like this. This is again an example from visual cortex, because that's what I do. This is the back of the brain. This is primary visual cortex. This is the spectrum when there's no stimulus, and this is the spectrum in the presence of a stimulus. It happens to be that stimulus. And you see this narrow band spectral power increase around 50 hertz in the gamma band, and that's called a gamma oscillation. If you plot it on a log axis, the same data, I think you can see something that's not quite so obvious here, which is that in addition to this spectral elevation around 50 hertz, there's also this relatively broadband process. And the reason I mention that is in support of my point earlier that there may be multiple processes going on in one band. In other words, what's going on here around 50 hertz may be the sum of this asynchronous broadband process and this narrowband oscillation around 50 hertz. And if we just measure the spectral power here, we may be mixing together two kinds of responses. Moreover, if we show a different subject to the same, a different stimulus to the same subject, same electrode, we get a very different spectrum. I'm not going to talk about why that is, but if someone's interested, you can ask me afterward. I just want to point out that we have this broadband elevation here, and if you were to characterize the response by measuring the gamma band power, you might say, well, I see some here, and I saw some here, so I guess all these stimuli are producing this response. But if you try to dissect the spectra in terms of component processes and say, well, I think there's a broadband thing here plus a narrow band thing here, and only a broadband process here, you'd arrive at a different interpretation, because the biological interpretation for what causes these oscillations is very different than the interpretation of what causes these broadband spectral changes. So in contrast to, this is kind of my straw man, but I see this all the time in reviewing papers. In contrast to the concept of summarizing a response by the sum of the band-limited power, you might try to come up with a model. This is one we came up with. It's extremely simple. It's a line plus a bump. Okay? A straight line in log-log space plus a Gaussian bump. But still, it lets us separate the response into two components within the same band. And it actually changes the way we interpret the data. Another thing you could do, as I showed you, is principal spectral components to try to use the data to figure out what the rhythmic motifs are. I prefer this one if I have a pre-existing hypothesis about what the distribution should be. You might as well use your prior knowledge. If I don't have such a assumption, then using the data to try to figure that out is a good alternative. Okay, so I'm now going to try to do something in 2 minutes that is going to be a little bit of a challenge. But I want to finish by talking about the two methods that are widely used to study the human brain. ECoG, which I use as a proxy for any of the electrical measurements like EEG, or fMRI. And I want to show you a plot that you might have seen before. This kind of plot is shown very often. Something like this, which shows the spatial resolution and temporal resolution of different instruments for measuring the brain. MEG and EEG have better temporal resolution. Functional MRI has better spatial resolution. And ECoG would be maybe over there. What I want to point out, though, is that these methods don't just differ in their temporal and spatial resolutions. In fact, they combine signals in fundamentally different ways. And this is a quote I got from David Heater, who said to me in conversation about a year ago, they differ in the order of operations. And that's going to relate to some of the things I talked about so far. And I'm going to have one slide with math to explain this. I'm going to try to hash this out in calculations. If I do something wrong, you can blame me and not David. It's a toy model. It's definitely wrong, but I hope it's useful. And so I'm going to assume that we have a population of n neurons. And we show the subject who owns those neurons a stimulus. And in each neuron, we measure some time-varying membrane potential in the dendrite. Call it V1 sub t, V2, up to Vn. And now we put an electrode over that bit of cortex, and we measure the summed response. Well, each neuron is going to contribute this signal times some value that reflects the fall-off with distance and the volume conduction. For simplicity, and I'm going to have to do a lot of things for simplicity, I'm going to assume all the neurons are the same distance away from the electrode. And that means all the C's are the same, and that lets me say that the ECoG response is just C times the sum of the time-varying membrane responses. And that gives me a whole bunch of numbers, because ECoG of t, that's a time-varying measurement. Maybe I've got 1,000 measurements in a second after I show a subject a stimulus. What am I going to do with that? I want to summarize that, and maybe I will choose to summarize it by computing the total power in the signal, which is equal to the variance in the signal. So I've now got this summary metric of my ECoG signal, which is that it's proportional to the variance of the sum of the membrane potentials of all my neurons. And what about the fMRI signal from the same set of neurons at the same time? I have to make some assumptions, a lot. For example, the bold signal reflects energy usage, and the energy usage depends on the amount of fluctuation in the membrane potential. And a nice simple measure of fluctuation is the variance, which I've chosen for a sneaky reason. So I'm going to say the energy from each neuron is just the variance in its membrane potential times a constant. The nice thing about that is I can say, well, my voxel, which has all these neurons in it, is just the sum of all those variances. And what I wind up with now is something kind of funny. This is what David called, I don't know if he had this specific thing in mind, the order of operations differ. The fMRI signal is the sum of the variance. And the ECoG power is the variance of the sum. And those things are not the same. And in fact, I know precisely in what way they differ because I asked Wei-Ji Ma, and he told me. The way they differ is by one term, which is the covariance. Okay, the variance of the sum of some this is just a math theorem. It's exactly true. The variance of the sum is equal to the sum of the variance plus the sum of the covariance of all the other terms. And the interesting thing about this, we're almost done, by the way, is that this is what I call the ECoG power. This is what I call the fMRI, the bold signal. And I have this other term. What's it doing there? If I try to correlate this and this, I'm just ignoring this other thing. And I don't want to do that, among other, because it's there. And also, this has a lot more terms than this. If this has n terms, this is n squared terms. It's a lot bigger, potentially, depending on the values. So can we unmix these signals? Well, to take your example, can we take 7 and figure out what two numbers combine to produce it? The answer is no. But we can make a guess with some assumptions. And this is going to take us back to the beginning of the talk, and then we're going to end. The hypothesis is that the broadband ECoG response that we measure is really capturing this, because it's capturing something that is asynchronous across the neurons. And that's what that signal is, that broadband signal. And that the rhythms we might measure, narrowband rhythms or steady-state visual evoked potentials or things like that, reflect something about the covariance, the correlation structure of the neurons. And so if we can separate our spectrum into a signal like this and a signal like this, we may get one part that correlates with the fMRI signal and one part that doesn't. And it turns out that that seems to be at least approximately true. And I believe this is my last slide, except for conclusions. It's approximately true in the sense that if we measure the broadband amplitude with ECoG for a bunch of different stimuli, and we measure the fMRI response in different subjects, same stimuli, same cortical locations, we get a very nice correlation. If we take the narrowband amplitude of the gamma signal and we correlate that with fMRI, no correlation at all, unrelated, even though in the spectral domain, this looks like a really big signal. I've offered an explanation for why that might not correlate. I hope that that made some sense. If it didn't, ask me afterward. So a few conclusions. The spectral analysis of ECoG data can be a useful tool to dissect circuit motifs, like the steady state signal, narrowband, broadband signals. They do not correspond one-to-one to frequency bands. Some ECoG responses span many bands, like the broadband signal. Some bands may contain multiple responses. And even a simple model-based approach can help clarify the circuit responses, like a line plus a bump. Finally, field potentials and fMRI combine neural signals very differently. The asynchronous broadband component of the ECoG signal is likely to correlate with the energy consumption and hence the fMRI signal. These are people who I have collaborated with, and I know I made up a lot of stuff in my model that are wrong. I hope it's useful. Thank you for your time.